Okay. Can you hear me? Okay. Yeah, it would be fun. Okay, this is continue. Oh, I should tell you first that the lecture note is updated every day, so you should probably download the new version. I add some explanation whenever it's not clear. I put some more explanation in the notes so you guys can go back and read it again. And secondly, for general recommendation, I mean, okay, I know that, for example, material yesterday was a bit abstract, and for those, especially for those of you who are not so familiar with superfields and so on, my general recommendation is follows. If you don't understand superfields, try to go in components and do things in components, okay? I will try my best to write every equation, both in superfield and in components. Do it in components. It's just a normal field theory that you learn, and then supersymmetrize it later, okay? This is general recommendation. But then, if you have problem, I'm here. So please feel free to come to talk to me. And yesterday, we talked about Gaugino superfield. Again, it's a superfield, so I'm sorry, but we write down components, right? So this is it, and we introduced the concept of holomorphic gauge coupling yesterday. So this is the one. And today, we're going to talk about one-loop beta function coefficients. So basically, we know that G runs, right? It's a gauge coupling, real. Okay? And this is the formula for the one-loop beta function. This is standard. And the coefficient B0, we put minus sign here, okay? And the coefficient B0 receive contribution from, this is the gauge field, this is from the Y fermion, and this is from a complex scalars. And these are Dynkin index, right, of each representation. So since Y fermion and a complex scalar can be in any representation, you have to compute these guys and plug it in, okay? Now, very good. So if I have n equal to 1 theory, what's a beta function? What are B0 here? Okay, so let's do it step by step. So you have gauge field, 11/3. Okay. Now, what is in the vector multiplet of the n equal to 1? So let's do multiplet by multiplet, okay? What else is in the vector multiplet? It's not just gauge field. There's gaugino, right? Come with a gauge field. So how does gaugino contribute? This or this? This one, right? So you have minus 2/3. Okay? And then you have the index of everything in the adjoint representation. This you agree? This is the vector multiplet part. Everything is in adjoint. Now, the chiral part consists of what? Scalar and the partner, right? Phi and psi. So phi contribute what? Phi contribute 1/3 and phi contribute 2/3. Okay, so this is I in the chiral. Multiplet T of Ri. This you agree? So to simplify, B0 is just 3 times adjoint minus sum of I in the chiral T of Ri. Okay? So this is going to be beta function for the n equal to 1 theory. Okay? Now, let's do an example. Okay? Let's take SUN for the n equal to 1. SUN gauge theory. With NF chiral multiplet in the fundamental of SUN. See? NF chiral multiplet in the anti-fundamental of SUNC. Does this smell something familiar? Look like QCD, right? It's a supersymmetric version of the QCD. So this theory is known as supersymmetric QCD. Of course, yes. And this is known as SQCD. Okay. So what would be the beta function here? Well, just plug in the number. So B0 would be 3 times T of the adjoint, which is NC, minus 1/2 NF plus 1/2 NF. 1/2 come from that the fact that Dynkin index for the fundamental and anti-fundamental are both 1/2. Okay, this we stated it last time. Okay, so it's 3 NC minus NF. This is important, so please bear this in mind. We will use this a lot. Okay, if you put NF equal to 0, it's just 3 NC. Okay, now we are ready to move on. This is just to recap the notion of a beta function. Okay. So I just take a Peskin and Schroeder formula, plug in multiplet in supersymmetry, nothing more. Okay. So now let's move on to the topic which is crucial for us. So we will do another important exactness in supersymmetry, namely that the holomorphic coupling, the TOR that we wrote there, is one loop exact in perturbation theory. Okay, this is a, yeah. So TOR appears in the action as a background chiral superfield. This we emphasized from the first lecture, right? That you should promote every coupling to a background chiral superfield. Okay. It must run and stay holomorphic. Okay? So what I mean is that if you compute beta of TOR, okay, which by definition is log mu. Mu is a renormalization scale, as usual, of the definition there. This must be holomorphic in TOR. Okay? So I just use holomorphy. Holomorphy is really powerful too, as you have seen. Okay? So how do we proceed from here? Okay. To show that beta, so what I will do next is I will show you that beta of TOR is one loop exact. Okay? So to proceed, there are 2 steps you have to do. Okay? So first step, I will show that theta doesn't run. So claim theta does not run. What do you mean by does not run? It means that it doesn't get renormalized. At any order in perturbation theory. Okay? So let's do the argument, the reasoning for this, why I claim this. Okay? So the claim is that any shift in theta, namely, if I do theta goes to theta plus alpha, this is a shift in theta. Suppose there is some shift occurring. Let me use A. can always be absorbed in this one is anomalous, okay, but we don't care. Phase rotation of a massless fermion. So if you have a shift, suppose that there is any shift in theta, you can always absorb it in the phase shift of the phase rotation of a massless fermion. I will show this, of course. But this is why it doesn't run. Because any shift like this, you can just absorb it. Okay? Now let me give example what is anomalous phase rotation mean. Okay? We can be very explicit. As an example, for Gaugino, in the vector multiplet, shift the phase rotation of the fermion is a symmetry, right? So this global symmetry is known as the R symmetry. So what is R symmetry is rotate the phase of the Gaugino, basically. So lambda goes to e to the I alpha, for example, lambda, okay? It is associated with the current J mu to 1 over G square lambda bar A sigma bar mu sigma bar lambda A mu. Okay. So this is the, for example, this if you have Gaugino, definitely this symmetry is there. Okay. Right. So now let's go through the argument. Okay. Is known as known. Sorry. Yeah. No. Other field can rotate because this is R symmetry. If you have other field, if they're charged, they get rotated according to the according to their R charges.
Yes.
Okay.
But also in the case I have just the Gaugino.
Yeah, if you have Gaugino, this is definitely. If you have no Gaugino, other fermion, you can always put the combination of the symmetry. You remember the various U1 we have? So you can make the field have charge 1 and then rotate it. The important part is that they always U1 symmetry to do this job for any massless fermion. Okay? Quantum mechanically, this U1 symmetry is anomalous. Okay? It is anomalous, but it's a global symmetry, anomaly of a global symmetry, so you are fine. Okay? This is known as the axial symmetry. Could you raise your hand how many of you know axial symmetry from the J5 mu from Peskin-Schroeder? Okay. So my derivation will be parallel to that. It's just in a supersymmetric context, okay? So, meaning that the associated current is not observed. Okay, so d mu, j mu equal to, this j is the symmetry correspond to this U1, the current corresponding to this U1 symmetry, okay? T of adjoint over 16 pi square trace F tilde. F tilde is just the star of F, if you want, okay? So, you're familiar with this, I hope, right? Okay. If you're not, okay. Oh, for those of you, can you tell me which triangle diagram you should consider? If I write this on this formula, it's come from a triangle diagram, right? So there are 3 corners. Which current you put in? 2 gauge and 1 J. Correct. That's a triangle diagram correspond to this anomaly. So this J is this U1 symmetry, and then 2 gauge current, okay? And you compute fermion in the loop, and that's it. This is the triangle anomaly. Okay. Now, if you learn, there is a method of anomaly called Fujikawa, right? So this corresponds to the shift in path integral measure. Okay, so let's do this board. So you see, it's a generalization of J5. This basically, instead of J5, we just have this U1. So it's the same phenomenon. So this anomaly is equivalent to changing the path integral measure which amount to shifting the Lagrangian by alpha t adjoint over 16 pi square trace F tilde. This is Fujikawa way of viewing it. If you're not familiar, I would derive this, okay? But take this for now. And for those of you who are familiar with anomaly, this should be familiar to you. Okay?
Sorry. Can I ask you a question? I noticed, okay, in general, if I have like a Lagrangian with a massless sphere which enjoys a U1 times U1 symmetry, like let's say the vector 1 and the axial 1. Now, is a symmetry like is a symmetry corresponding to U1? I mean, it seems to me that there are 2 different symmetries, no? Like, why are we considering the other?
There is a single U1 for now. Suppose you take pure gauge theory. Forget about matter for now, okay? If you have matter, you can have a vector like U1 also. But if you have a pure gauge theory, let's say, no matter, you have only this U1, and this U1 is anomalous.
So this is U1 R symmetry?
Yes. If you have only gaugino, only vector multiplet in your theory, it will become clear to you. This question, could you wait?
Yeah, just because... Like,
I will add matter later, but with pure gauge theory, no matter, there are only this U1.
okay, under this U1 R symmetry, doesn't the other field change as well?
What is other field?
In the model?
There is only gauge field and the gaugino.
And which field?
Yeah, the gauge field.
Okay, that doesn't...
No. So basically, you have this component, but gauge field is not fermion, so it doesn't contribute to anomaly.
No, because the current there was only one part of the current. If there was also the other gauge.
Let me add matter later, and you become clear to your question. Okay, let me proceed for now. Okay. For those of you who are not familiar, I will do this later, okay? And matter will come later. I will tell you how to deal with when you have anomaly in matter, in the theory with matter. Okay. So, if you stare at your Lagrangian, you shift the Lagrangian by this amount. In the Lagrangian, you remember there is a term which is called theta over 32 pi square trace f tilde. There you go. You can absorb this in the shift of theta. Okay? So observe that this is equivalent to the following shift in theta, where theta goes to theta plus a. With a, now you can identify it as 2 times adjoint times alpha. So this is how you relate that alpha to this a. So for which the relevant term in the Lagrangian is shifted as follows. So you have this term, this is the relevant term that I'm talking about. Of course, you shift by a. So what I'm doing is that the shift in the fermion, okay, the shift in the fermion phase is equivalent to, you can absorb and shift in the theta angle. So hence theta doesn't run. Okay, this is finish of the argument that I want to state. Okay? Now, any question? Let's proceed to the second part. So this is the first part. You show that theta doesn't run. Now you can use a lot of things to do, okay? You use this result together with holomorphy. You can prove one loop exactness. Let me, probably this board. Okay. So with this claim, now we proceed to the second part. Beta tau is therefore independent of its real part. Because this guy doesn't run, right? So you can feel free to differentiate it. You get 0. Now what you mean is that you get d by d log mu theta over 2 pi plus I 4 pi g square. Look at this trick carefully. D by d log mu I 4 pi over g square equal to minus 8 over g cubed beta of g. Okay. Up to this step, see that this holomorphic guy has an I in it. But since it's holomorphic, it cannot be. Therefore, it has to be constant. Right? It has to be constant function. Okay? And this is due to holomorphy. And how do you determine this constant? From one loop. Right? It's one loop. It's run at one loop. We just show it. So, This is just I over 2 pi B0. So this is due to holomorphy. And since it's constant, this is due to one loop result. You plug in the formula that I stated earlier, this one. Recall that the beta G at one loop is minus B0 G cubed over 16 pi square. You plug this in, you get this. You see this? So this is how to show that it's exact at one loop. This is due to holomorphy. And the proof really rely on the no running of the theta.
Sorry, you want minus 8 by I divided over G cube or?
Yes.
Oh, okay.
Yeah. Okay.
So this fact that on the running holomorphism is not messed up, is that an obvious thing or is it?
No.
It's really inputs.
No, this is not highly non-obvious, highly non-trivial result, right?
Okay. But I mean, could it be that some cheat code messes up holomorphism?
No. Unless you can show that your theory violate your holomorphy. No, not in 4D n equal to 1.
But there could be examples.
I don't know. I'm not aware of. I think this is very solid. If you believe that holomorphy preserved, which I state very clearly, the I assume the beta tau is holomorphic, right? Yeah. So if you violate any of my assumption, of course, you can, in the future, you never know, but I don't think this is very well established result, at least up to, since this result is really old, from the 70s, 80s, I mean, no. Yeah. Okay, let me comment. Non-perturbatively, it can receive a lot of correction. We have a lot of example, but in particular 4D n equal to 2. If you go to, this is a bit more technical, you can use modular form to constrain the non-perturbative correction in 4D n equal to 2 gauge theory, but not n equal to 1, I mean, well, let me state that it's perturbatively is exact to one loop, okay? So now let me proceed. Beta of tau is perturbatively one loop exact. And I would like to emphasize again, this is only true for holomorphic gauge coupling, not the real gauge coupling G. Real gauge coupling G runs to high order, okay? This is only beta of tau. Now we come to this point. Let me derive another important result, okay? Any questions so far? Okay. Let's assume that beta 0 is not 0, okay? So, you can integrate this equation further. So you have I4 pi over G squared. Now G depends on mu, okay? Equal to minus I over 2 pi. Beta 0, once you integrate, you would get an integration constant, right? Let me call it big lambda. So log of big lambda minus log of mu. You agree with this? It's just coming from integrating this equation. Okay? So meaning tau, which is by definition this guy, will be equal to I beta 0 over 2 pi log of lambda e to the theta over b0 over mu. Okay? All right. We define a complex number lambda equal to mod lambda e to the I theta over b0. Okay? And obtain e to the 2 pi I tau mu equal to e to the minus 8 pi over g square. Of course, it's a function of mu plus I theta equal to lambda over mu b0. Who can tell me what this phenomenon called? Dimension transmutation, correct. Why?
I changed the dimensionless coupling to a dimension full dimension.
Exactly, thank you. This is very good. So this is dimensionless, okay? But now you appear this dimension full, okay? So you trade it. Now the point is that this is in parallel to QCD. If you remember, in gauge theory in 4 dimensions, G is dimensionless. But quantum mechanically it runs. So quantum mechanics destroy the scale invariant, okay? So this is the same phenomenon in supersymmetry. Observe that this is complex. Hence, you should promote it as a background field, as usual. Or coupling, or energy, or scale. This, you should promote it to holomorphic quantity. You will see that it acquires R charge. Okay? You will see that later. Okay, now.
At the bottom of that door, from holomorphism, you can claim that beta function is G cube exact, right? Not necessarily one loop.
What do you mean? It's what?
Yeah, here you said one loop exact, but I think what you can actually say is this is G cube exact.
It's a
G cube.
but that's one loop.
Yes, but I mean that is true in this case. For instance,
It's gauge theory, so it's one loop is G cube. I just stated.
yeah. So, but
Okay, call whatever you want, okay? Call it G cube exact.
yeah.
Okay. Right. Now, second thing I would like to point out here. You see 1 over g squared above exponential? This usually doesn't admit the Taylor expansion, right? This is phenomenon which is called non-perturbative effect because you cannot do expanding in a small parameter. This is called one instanton effect. Okay?
One question. Usually QCD is lambda is given by the fact of the side-side arc and the side condensation. So I guess the same should happen here.
Soon I will derive that.
So these are dynamics with otherwise.
Yeah. In the PON equal to 1, this phenomenon is called gaugino condensation.
I see.
Okay.
But sorry, isn't it true that in principle, chiral symmetry breaking and dimensional transmutations are two very different things?
Yes.
That for gauge theory, that's a
Here, chiral symmetry breaking is that U1 anomalous, right? This is my chiral symmetry. The chiral version in 4D equal to 1 version. Exactly. This is the supersymmetric version of what you said. Yeah. Now, also, it will be also true when you add matter, because now you have a chiral. I will show you, but later, okay? Don't worry, we will add matter. Okay. Any question? Okay, if not, let's move on to the pure n equal to 1 gauge theory. Now we can even focus on the interesting phenomenon. Okay? So let me summarize first. So we derive dimensional transmutation in supersymmetric version. It relies on two things. It relies on one loop exactness, okay? Because this tau, and we automatically get this as an integration constant, basically. So this is very nice, as you can see. And next we will start doing in a particular theory, okay? Namely pure n equal to 1 gauge theory. So, okay. Some people also call this pure n equal to 1 super Yang-Mills, okay? Okay, now let me write things in component for you. So S gauge is look like this. Okay, so basically this just looks like ordinary QCD but with one fermion. You agree? This is one of the reasons why people back in the day was interested in this. They hope that if you understand this theory, you might have a chance to understand QCD. Okay, turned out to be not quite true, but okay. Right, so let's talk about R symmetry. So our symmetry, this is a symmetry that rotates gaugino as follows, okay? The R charge is that gaugino contains charge. If you remember in my W, my next component is the F, contracted with sigma sigma, okay? So the R of FA mu nu sigma A alpha alpha dot B sorry, I put mu nu beta beta dot equal to 0, and R of the anti one is this guy, okay? Right. No, excellent question. Thank you. Usually in chiral multiplet, you feel free, unless there is a quantum effect who tells you, which I will discuss later. Classically, you can choose any R. This one, no. This one is fixed by the supersymmetry. So anything that you would like to call R charge, you have to assign 1 always to gaugino. There's no condition for that, okay? This is because, again, the structure of the superfield that I wrote down earlier. Okay, you know why? It's because gaugino superfield come with D2 theta. If you remember the S gauge that I wrote in superfield is D4x, D2 theta, trace WW. That fixes the R charge uniquely. So you cannot negotiate. Okay? And again, this is classical condition. Okay, but you have to satisfy even quantum mechanically, unless you insist that you break supersymmetry. Okay, now if you remember, This shift in the phase of fermion is equivalent to shift in the theta angle by theta plus 2nc alpha, or shift in tau to be tau plus alpha over pi nc. Okay? Hence, e to the 2 pi I tau, okay, equal shift by 2 to the 2 alpha nc I e to the 2 pi I tau. Okay? But remember, this guy, since e to the 2 pi I tau, oh, I still have that here, is proportional to the lambda b0. We see that you can assign the R charge to lambda also, okay, to be 2nc over b0. Yeah, so you better think of it as a background field. Okay. Now, next topic. We have seen that U1 symmetry that rotate the phase in a massless fermion is anomalous. Okay, we have seen that result. This is earlier. The point is that, okay, anomaly break this symmetry. So you have U1R, and you know that for pure n equal to 1, this is anomalous. So it's broken. Broken to what? This is my next question. Okay, and now we're going to show that it broken to, how do you call this? Z 2nc, the set of integer 2nc. So, okay, let me show this soon, okay? Okay, anomaly of the R symmetry. Okay, if you look at this shift e to the I alpha lambda, okay, and you look at the path integral measure, you see that the path integral measure, this is now how I'm going to derive the shift in the path integral measure, okay, of exponential e to the I alpha to the 16 pi square d4x dff trace TA of adjoint TB of adjoint. Do you agree with this? Because I just showed that this shift in the phase correspond to shift in this term. This is anomaly, right? This shift in the theta angle by this amount. You agree? This is what? Who can recall this? This is simply Dynkin index, right? What you call T adjoint times delta AB. Right? And for this is NC for us. Okay? So this is equal to d lambda exponential I alpha NC over 16 pi square d4x FA. Who have seen this thing before? This is called second Pointergin class, right? Or otherwise known as instanton number. And this is why we call it instanton effect. Okay? So let me state. So 1 over 32 pi square d4x trace f tilde. Okay, 4. This is equal to k, with k being integer. So this you can write it as d lambda exponential I alpha 2nc times k. Okay? And this means that you evaluate this integral in the k instanton background. This is how you call it. Okay? This is how it arises. Okay. Again, let me emphasize 200 million times that this transformation shift the theta angle by this. Just this, okay? Now, very important point. The path integral is invariant under, observe that because of this k, now it's integral, so you can play the following thing. The path integral is not just invariant under any shift, right? Because now the phase become integral value. So e to the 2 pi I n over 2nc lambda, where n is equal to 0, 1 up to 2nc minus 1. This action leave the path integral invariant. Okay? Where alpha, you can put alpha here to be 2 pi n over 2nc if you want. Okay? So now it's a discrete value. It's not continuous U1 anymore. Did you see that? So what I did show is that at this point, we see that the instanton effect break U1R to Z2NC. This is highly important result. Okay, this I promised to show you. What I showed you was that this, I showed you before, right? That is equivalent to the shift in the theta angle. But this is anomaly, so it's the same as a shift in the path integral measure. Now I show you explicitly what amount of shift you have to do. This I haven't done before, right? No. This amount of shift. I didn't show it before. What I did before was that any phase can be absorbed in the shift in theta. Okay? This part I'm computing to you explicitly, this shift in the path integral measure.
Yes, but if theta would run, and then you would have to add some other phase to the fermion that is not this very precise number that is preserved at the bottom level.
So you agree that any shift in theta you can absorb in the phase?
Yes, but quantum mechanically we just saw that not any phase is a shift.
No. Any shift, this is there. It's symmetry, but it's anomalous. Anomalous symmetry doesn't mean that you cannot do it. It just happened to be here. Anomalous means that you have two ways to view it, that the conserved is not current, the current is not conserved, and the path integral is shift. And that's how this shift luckily make you able to absorb any shift in theta. That's the whole point of this anomaly. Okay? So now, this is a key observation. Okay, so Yeah, but this is called breaking. This is called breaking. You originally in your Lagrangian you have U1R. There is anomaly, and you left with C2NC, which is non-anomalous. This is called breaking because C2NC is to act as an R symmetry because it rotates the phase of the fermion. This is we call breaking. If you don't like this terminology, you can call it anomalous and become C2NC, or C2NC is a symmetry that left over non-anomalous, but I call it breaking.
So one question. What happens in large n limit in that case? The phase seems to be undefined as it.
No, it's fine. It's exact. This is exact result for any NC. You feel free to take any limit you want. No, this is exact.
The path integral measure, at the end you come out with basically a quantization condition. Basically puts a condition on the sort of phase rotation that you can have on the path integral measure.
Yeah.
So does that mean that that is the only type of rotation that you are allowed to have in your action?
So yes, this is anomaly. Due to anomaly, you have only one fermion in this theory.
Correct. The U1R symmetry, is that actually a symmetry of your action? If it's not
It is. It is. U1R symmetry is the symmetry of the action. We showed it from the beginning.
But your path integral is only allowing you to have certain quantized rotations.
That's the whole point about anomaly. Anomaly means that you have symmetry, which is symmetry of the Lagrangian. Think of J5. This is symmetry of your Lagrangian, right? When you have this chiral fermion. And quantum mechanically, this symmetry is not the current is not a conserved current. So quantum mechanically, it's not a symmetry. It's anomalous. The current associated to it is not conserved anymore. It is symmetry of your Lagrangian. But this is a phenomenon of anomaly. Right? Think of axial anomaly that you're familiar with.
Yeah, I guess what's bothering me is that my path integral measure only has certain rotations that it can.
Yeah, yes, but this results in the fact that you can only rotate in the. That's why U1R become this.
Right. So yes, U1R is not a symmetry of the path integral measure.
Of the path integral, no. Of the action, of the action, yes. Of the Lagrangian, yes. Yeah. But yeah, this is Fujikawa, right? Yeah. Okay. So next, I will show that this is non-anomalous. This is a symmetry that become R symmetry of the theory. However, when you go to each vacuum, it can spontaneously broken further. You familiar with this? From the first lecture, I show you that there is a Z4 that rotate the two vacuum in the Westermino model. When you go into vacuum, it's broken to C2. You remember? Precisely the same thing will happen here. We have C2 and C here. When you go into each vacuum, I will show you that there are NC vacuum, and this symmetry spontaneously broken to C2. Okay, so let's do that. Okay. You agree? So we expect the gauge coupling runs. The theory is not scale invariant at quantum level. Okay. And you expect that lambda to the 3nc is dynamically generated. This is expectation because you expect that lambda to the b0, and b0 is 3nc. So you expect that this is dynamically generated. Okay? How? Why? Which generate this scale? Okay, so we use Seiberg trick here. So the great insight comes from QCD, of course, that you say that chiral symmetry is broken because there's a condensate of some bilinear. The only fermion in this theory that you have is lambda. So it has to be the condensate of lambda. This is the insight that you have, okay? Now to get it precise, I will show you. So since lambda to the 3nc has R charge, 2nc. This you agree, right? We derived the R charge of lambda before. It's 2nc over b0, right? So when you raise it to the b0, you get 2nc, okay? And has mass dimension. This has mass dimension 1 because it's a scale of energy, right? 3nc. The only object that is compatible with this is expectation value of trace lambda lambda to the nc, which is defined as trace lambda lambda x1, lambda lambda x2, up to, no, this is not what I want. This should be some constant, lambda to the 3nc. Okay? So this is just simply use R charge, holomorphy, and mass dimension to restrain this, to get this equation. Okay, there are some subtle points here. What is this C? This method will not allow you to evaluate this. This is point number 1. Point number 2, you have to trust me or trust other physicists that C is non-zero. Because if it's 0, what we just say is meaningless. Okay? So, if you are really pressing, you can even ask me, what is this C? I really want to know this C. What is non-zero? What is this C? I can only tell you that this is a huge debate. Now it's settled, I think. But, okay. In the history, let me tell you the story. This is in reference 18 and 19, if you want. Okay? In my note, people said, oh, I can compute instanton effect in this theory and get this C. The point is that this is strongly coupled theory. How reliable is a one instanton effect? There is, a huge debate among this. And so let me tell you, here is not important for us. What we're going to assume is C is non-zero. Okay? Go to the literature and read the reference. You will see that what is precise value of C. I will mention it later. Where you can do instanton calculation in a reliable and then obtain this C in the final form. But let me postpone it now. This is not important for us. We just assume the C is non-zero. Let me proceed.
If I see such expectation value, I would expect that it should equal a certain function for the space-time coordinates. Why should I obtain
This is my next point. Yes, excellent. I will show you that this doesn't depend on X because of the chiral field property. In general theory, you cannot conclude this thing, but in supersymmetric theory, you can. So the point is that okay, the quantity trace lambda lambda to the NC can be computed using the cluster decomposition. So this you're probably familiar. So you take trace lambda lambda to the NC, which is defined as above, and you separate them in a way that this xi minus xj is much larger than the scale lambda inverse. Okay? If you manage to do this only in this limit, in field theory, usually you can conclude that this equal to lambda lambda expectation value to the NC. Only in this limit. This is called the rule of cluster decomposition. Okay? So you separate them far away from each other. Then, if you manage to do that, then this result holds. Okay? However, it can be shown that, which I will show, since you are in advanced year, this is the time to do it, okay? It can be shown that this guy is independent of x1 up to xnc. Since it's independent, you feel free to do whatever you want. You can take them far apart, then this becomes an exact relation. Okay? Okay, let me tell you what's behind this. This is because these guys are part of the chiral field. And the OPE, the short distance operator product expansion of chiral field, let me emphasize, has no short distance singularity. This I will prove, okay? Because of that, you can, it doesn't depend on the distance between the position that you put in this operator. Okay, so let me write it down.
Sorry.
Yeah.
But you said that there is directional transmutation, and so the theory becomes gap. How can you use the OPE? How can you say that the OPE converges at all?
The point is that, wait a second, and then you tell me when the flow of the proof is, okay? Wait a bit, okay? 15 minutes, okay? In ordinary gauge theory, you cannot do it, but in supersymmetric theory, you can. And this is related to yesterday also, when we do OO bar. This is why dagger gives you 1 over something square. If you do OO, there is no such thing. Okay? In fact, so let me put this in remark, okay? Trace lambda lambda is the lowest component of the chiral superfield. S equal to trace W. Okay? Do you agree that this is a chiral operator? So do you agree that this is the lowest component? Because W has a lower component being lambda. Now you contract two of them. You get trace lambda lambda. Okay? This has a name, S. Some people call it glue ball superfield. Okay? Since the product of the chiral superfield has no short distance singularities, the former statement follows. Of course, I will show this more explicitly later, but this is the reason why we can, this is why this is independent of the position.
Sorry, maybe you studied and why it doesn't have short distance singularities?
I will show it.
Usually when some quantity does not depend on the position of the space-time, we can also think that
I wouldn't call it the topological in this sense because this is a correlation function of the chiral field. This is particularly solved for this one. I mean, in general, I don't think this is any way topological. But if you want to compute something interesting that have singularity, you have to do with anti-chiral, such as O dagger that we did earlier. And that's why O dagger leads to log singularity. And this explains why this thing doesn't lead to singularity, you see? So running of the coupling coming from the O with it anti-chiral, yeah? O tilde, O dagger. This one doesn't lead to singularity. So this means that we can always take separation between xi to be large, to be larger than lambda inverse. Okay? So what we have is that trace lambda lambda to the nc equal to 3 lambda to the 3 nc. Now, come to very important result. You take the nc root. Then you have trace lambda lambda is equal to c tilde lambda to the 3 c to the 2 im over nc. Okay? C tilde also non-zero. M goes from 0, 1 up to n minus 1. And since now evaluate this in each vacuole, right? So the vacuole is labeled by M. And it's a discrete vacuole. 0, 1, 2, up to nc minus 1. So you have in total nc vacuole, and these label the vacuole. So we put M here, okay?
Can they just start with trace lambda lambda and say that by dimensional analysis at the Archer designation can just...
Yeah, you can cheat the way through, but then you can ask, is this a trivial result? Right? For me, this is highly non-trivial in the sense that you have to show that there is no short distance singularity. What you can show is the expectation value to the NC is compatible with that, but not more than that. I think. Okay, right. So what you have is that you have NC vacuole. this is also power of the superfield in some sense, okay? If you ask me, is there a short way to derive this thing, I would say it's very difficult. This is very easy in superfield language, as you will see, okay? Okay, so you have NC vacuum labeled by M to NC minus 1. So now I show that the vacua are discrete, okay? Next, since in each vacuum, trace lambda lambda not equal to 0 is invariant under, you agree this label the vacuum, lambda goes to minus lambda. So you see the rotation of M even now reduced to a phase. Okay? Well, or you can write it in the long-winded way like this, where alpha is equal to 0, pi, 2 pi, up to you. This is equivalent statement to before, okay? So, condensation breaks Z2NC to Z2 in each vacuum. In each vacuum, okay? So this is another important statement. Okay. Now, I hope you see now why I did the example of West-Sumino model in parallel now. This is the purpose that now it's a much more complicated model, you see, of the very similar phenomenon where you have vacuum and you, yeah.
I ask a specific question about factors because last time we had one Carol multiple with no H and we had C4. Right?
Yes.
And I would kind of expect 2 times 1 is not 4. So, I mean, if I take this general formula that I break U1R to C2 and C, then I would expect breaking U1R to C2 instead of C4.
So that U1R that we have initially, when you pick a particular charge and so on, right? Yes. That was, you see the C4, you agree with me with the previous discussion. Yes. Here is 2NC because of instanton. And of course, we don't have instanton there. We don't have even gauge field there. Yeah. But it's a similar treatment in the easy, that was easy example. This is harder example. Sorry? You predict my next section. Of course, this is an old question of Witten. Let me address your question in the next section, okay? I owe you many answers, so I have to show also the trace WW are permuted. In fact, if you read my notes, it's probably answer all of your question already. Yes, okay. Now come to the important point, that these NC vacuum are permuted by the C2NC symmetry, because equivalently to the shift theta goes to theta plus 2 pi. The generator of 2NC Z2NC, send mth vacuum to m plus 1 vacuum and multiply trace lambda lambda by e to the 2 pi I over nc. Okay, so yeah. Okay, so let me say the rest in word, okay? So there are 3 expectations about that the theory has a mass gap. Mass gap means that there is no massless state, okay? Because these are dynamically generated, so you have a gap, okay? And believed to lead to confinement. Of course, this, yeah. So second one is that second is the theory has confinement, and the third one is that there is a phenomenon that look like chiral symmetry breaking that break Z2NC to C2. Okay, this is very similar to chiral symmetry breaking. So you can see that there is a very similar feature with the QCD, and this one you can show something much more exactly. At least you can determine this scale and so on. Okay. Now you can ask me, if I change the gauge group, what happened? Oh, to answer your question, it is supersymmetric vacuum. There is no such, there's no, we call it dynamical supersymmetry breaking. So in the old day, people ask this question. This is strongly coupled effect, highly quantum mechanical. Very few computation can be done. How do you know that upon flowing renormalization group flow, you don't break supersymmetry? Okay, so this is come to another tool called Witten index that he can show that it's a non-zero. Hence, supersymmetry is preserved. So this is the next topic that I will do, but let me state one crucial statement. This is a 20-year-old problem. Also, Witten solved by himself. It might look trivial for you, this statement, okay? But for a general gauge group G, well, you should assume it to be connected, simple, and simply connected. There are H check to G vacuum. This number is called dual Coxeter number. For example, if you have SONC gauge theory, let's say assume, or spin, okay, because S always has an issue. Spin NC gauge theory with NC greater than certain number, this is NC minus 2, for example. This is the number that I'm talking about, okay? And why this is a hard problem? Because this number NC that you saw, we have NC vacua, right? This is dual Coxeter number of SUNC, okay? So you'll find with that. It's the same as C2 of a joint, okay? Now, when you people used to think that this is the rank of SUNC plus 1. Historically, this is in the 80s. Witten himself wrote a paper. He showed that, oh, this is look like a rank plus 1. But when you generalize to other group, it's not true. He corrected himself 20 years later, by himself. This is the reference that I put in the note, okay? So first Witten paper on this is 82. Then it's in reference 21. I can give you a timeline. 21 is 97. 82 and then 97. I wrote 2 papers to recognize this fact, to reconcile with this fact, okay? It's highly non-trivial. Okay, So I don't think I have time. It's in my note, by the way, of that subtlety why in 82 paper there was some missing link, but he corrected himself in 97. So this is in the note. I will give you a brief explanation, but not explicit derivation because I have no time, okay? Now let's do what I promised. How much time do I have? Half an hour. You want a break? Okay, then let me. Okay, so let me derive at the trace condition that it doesn't depend on x, and we take a break. Okay, then we do with an index. Okay. So for those of you who are scared of superspace, I'm sorry, I need to use it. But for those of you who have no, so you can sleep if you don't want to hear about superspace anymore. But for those of you who are interested, this is gonna be the show why to demonstrate that. This guy is independent of x. Okay? Okay, so do you agree that W is a chiral field? But not gauge invariant because it carries the gauge index A. Okay? Okay, so what you have is that dW alpha, well, you can use beta equal to 0. Okay, so you define a quantity, WW, trace W square to be usual guy. So you must have d alpha dot trace of W square equal to 0. It's also chiral. Okay? Now you use the definition of a superspace derivative. So recall that minus 2i sigma mu alpha alpha dot d mu x mu equal to d alpha dot bar. Okay? So you will conclude that 2i minus 2i sigma mu alpha alpha dot d mu of trace W square is equal to, because of this commutator, whenever d bar hit trace W is 0. So you have this. Okay? For any scalar operator x, the one-point function has to be 0. Why? Because of Lorentz invariant. You cannot have index because this is scalar operator. Okay? Now you use the fact that this is d dot bar of whatever inside here. So if you compute expectation value, it has to be 0. Therefore, this is 0. Okay? Using you can show that this guy for any j. Well, you can put n here and then n here. Okay? Now you take lambda. Lambda is the lowest component of this, so this has to be true. So I finish my proof. So did I cheat?
Where do you use that? What you can show is that one-point function of some non-scalar thing is zero.
But this is scalar.
Right. It's not a one-point function. If it's a correlator, you act with the x mu, you can use that it's the alpha dot of something.
What is not scalar?
It is a scalar, it's just not a one-point function. It's a correlator. So
Okay.
you act with the derivative, say with the first operator.
But it doesn't care what is this, right?
That's true, but it only vanishes if it's a one-point function.
Okay.
So take the derivative and act on, say, the first operator. How can I see that?
I'm computing this, right? What's your problem? I don't see it.
My problem is that you can make the expectation values of non-scalars vanish, but it's not
Okay.
an expectation value, it's a correlation.
Okay.
So why does it happen? I mean, once I think that your idea is that you have this space-time derivative, you have
Yeah.
to say the first operator.
Yeah.
Then you can replace it by the alpha bar
Yeah.
of something.
Yeah.
But why does that have to vanish?
Okay. So you disagree with this x?
No, for the scalar operator, that's okay, though. We're just saying that what we're computing is not scalar.
So you mean that this is not an x?
No, what we're computing above is not scalar.
Let me see. Can I do?
It's not. It doesn't depend on multiple points. It doesn't matter to me. One-point functions have to vanish here, but it's not a one-point function. It will depend on multiple things.
I look at this as a scalar operator. If you have a problem, we can discuss this later. Okay? But this is the idea that I use. I put this in the x.
How you can match the index of the
Hmm?
The point is that how you can match, if it's not zero, how you can match the index of the dot? You have only coordinates that must be another index.
Oh, so I use this, let me see. So you disagree with the, Okay, let's take a break. And if you have any question, you can ask me.